If the universe is infinite and billions of years old, where are all the aliens? This simple question has led to a paradox that has been debated by all science lovers on this planet for 100 years. Every year, there is a new revolutionary solution to the paradox of no traces of alien activity. Crazy concepts are proposed, scientific theories are created, and thousands of videos are released. But in fact, the answer to Fermi's paradox was given in 1933, even before Enrico Fermi himself stated the paradox. The short answer is Australia. For details, let's go back to 1933 and meet Konstantin Tsiolkovsky. The self-taught scientist was born in 1857 and spent much of his life laying the foundations of theoretical cosmonautics. Satellites, ballistic missiles, interplanetary reconnaissance, and everything we see now, Tsiolkovsky theoretically brought it to the public. He was the first person in the world to centrifuge 300 times the weight of cockroaches, and proving that space exploration does not harm humans. In fact, it's not for nothing that SpaceX's largest conference hall is named after him. In the context of the Fermi paradox, Tsiolkovsky is interesting to us because he is the real author of the paradox. Are we the only intelligent and technologically advanced civilization in the universe? Enrico Fermi asked his famous question in the summer of 1950 in the cafeteria of Los Alamos Laboratory. The paradox is named after him, but Tsiolkovsky posted it 17 years ago. In 1933, 2 years before his death, Konstantin wrote a philosophical treatise that received little attention. It was later published under the title Planets Inhabitable. In his writing, Tsiolkovsky analyzed the same question that Enrico Fermi would later ask. And it is also very logical, scientifically sound, and up-to-date answer. First, Tsiolkovsky was clearly visible. His article begins with the statement, "It is absolutely impossible to doubt the existence of countless planets." The argument is iron. Tsiolkovsky notes that all celestial bodies obey the laws of gravity, light, gas, and other physical parameters. That is, the planets of other systems differ from Earth only quantitatively, not qualitatively. They can be of different sizes, denser atmospheres, longer or shorter days, and things like that. But qualitatively, the laws of physics work everywhere. What is the basis for believing that the origin of life was some process unique to Earth? Tsiolkovsky logically shows that hundreds of thousands of chemical processes in the universe operate according to the same laws. Given the abundance of planets, somewhere they will lead to life. The only question is when and where. Tsiolkovsky then moved on to solving Fermi's paradox. The universe is billions of years old, and many believe that traces of aliens must have been left behind. This is where Australia comes into the picture. In the article, Tsiolkovsky gives a philosophical answer. The Aborigines of Australia lived separately for tens of thousands of years. Were they right to say that there is no life outside of Australia because they have no evidence? Of course. Tsiolkovsky's philosophical spending could extend to Europe, where he also doubted that the Americas had been on Earth for tens of thousands of years. Besides, we are not talking about historical figures. By the 14th century, there were already pistols, surface-to-surface missiles, air communication between troops, and printing machines. And yet, these pioneers were unaware of the existence of America, 2,000 miles across the ocean. Calculations can be supplemented with scientific data. Homo sapiens settled in Australia about 65,000 years ago. And for 60,000 years, they were isolated. Only 5,000 years ago, they were the first to arrive on the continent and gave the Australian Aborigines a modern look. Formal colonization of the continent began in the 18th century. It was thousands of years before Australians learned that there were civilizations on other continents. What makes us think that alien civilizations exist for those of us who are taking the first timid steps in space exploration? We have a photo of Neptune, which by cosmic standards is in our backyard, taken 3 times. The ancient Australians built a boat 100 meters from the shore, explored a small island, turned back and said there was nothing interesting. It is presumptuous to say that our level of technology is sufficient to detect extraterrestrial civilizations. From a historical point of view, it is more correct to say that we are still less than Selenotes. We can put Tsiolkovsky's words into a different context. Suppose aliens visited Earth 10,000 years ago, even by human standards. This is recent. If we imagine the life of Homo sapiens as 24 hours, our hypothetical aliens were on Earth only 1 hour ago. Can we find any evidence? Of course. In such an accounting system, you and I have effectively lost all knowledge of the written language of the Minoan civilization, which lived 10 minutes away from us. Sumerians, Osirians, Acacias, and other civilizations are a bit older than us. Nevertheless, archaeological discoveries are becoming more interesting every year. On June 6, 2022, a 3,500-year-old inscription was found on a clay tablet in Israel. It is 400 years older than the officially recognized alphabet. And, no doubt, in the next few years, the date of the appearance of writing will move back several thousand years. What if there are records somewhere of aliens visiting Earth? This is theoretically possible. It is important for us not only to talk about space, but even about our native Earth, which we cannot talk about in the absence of a foreign visit. The most reliable history of the Earth, as we know it, is the past 1,000 years. This is less than a percentage of the lifetime of Homo sapiens. If we are talking about the Earth as a whole, it is not even dust. No, we are not saying that the Egyptian pyramids were built by the Anunnaki and the Great Wall by Slavic Jedi. We are talking about hard facts. We only know about a small moment in human history. From a scientific point of view, we cannot say that there is no evidence of aliens on Earth. Here, of course, we can recall Russell's teapot, and lack of evidence does not make a theory wrong. But Tsiolkovsky has another proof of this effect. This is a famous zoological theory. We don't go to wild bears, gorillas, or snakes. It doesn't make sense because we have nothing to talk about. If such a layer exists among organisms within the small Earth, why should it not exist within the infinite universe? We can't rule out the possibility that we know about them, but don't understand why they should talk to us. On Earth, we isolate endangered lions in reserves so that their civilization is not disrupted. Perhaps we ourselves are a small civilization by the standards of space, which is of no interest to anyone. Often in response to this theory, you may hear the question, but where are the super civilizations? After all, they use too much energy to hide. If some advanced civilization uses solar energy, it's easy to find because Earth's light will be weaker in the optical range and stronger in the infrared. Stronger. In theory, modern telescopes are sufficient for this. However, we do not see any signs of such anomalous behavior of the stars. Sounds logical, but this theory does not stand up to fact-checking. What makes us think that advanced civilizations use a lot of energy? We derive it from the ideas of modern physicists about the rapidly increasing energy consumption of mankind due to the increase in human population. But in reality, the picture is a bit different. In 1970, the United States, with 200 million people, used 13 trillion kilowatt-hours of energy per year. In 2020, that number was 24 trillion, with 330 million people and insane advances in technology. Now there are more people. Everyone has dozens of gadgets, and somehow less energy is used. The situation is very similar to the agricultural sector. In 1970, the United States had 2 acres of land per capita. In 2020, it is more than 1. Are we eating less? No, of course we eat better than ever. The answer to the puzzle is the same as in energy. As mankind developed, the efficiency of both devices and production increased. Nothing can grow fast. Our reactors are better, our farms are more efficient, and that's the trend right now. Moreover, the population is not expected to increase in the near future. On the contrary, all available evidence shows that the higher the standard of living, the fewer children they have. Therefore, it is more logical to think that there will be fewer, rather than more, aliens with superpowers. And they probably don't feel the energy, but they get wildly effective. Of course, this is just a theory, but it has as much right to life as theories about Dyson spheres. Its absence is said to be the cause of Fermi's paradox. Tsiolkovsky does not go into such details, but he notes in his article that we cannot talk about the absence of extraneous signals. We don't know what these signals might be. For example, a highly developed civilization could theoretically explode the star SN 1987A in an interesting way, which was observed on Earth in 1987. How to distinguish between natural and artificial processes in space? Scientists still don't have an answer, and so we can't say we haven't seen any signs of alien activity. In conclusion, Tsiolkovsky's answer to the Fermi paradox tells everyone to look in the mirror. We humans kill each other, start wars, and abuse animals. How do we treat aliens and not see them as competition? According to the scientist, the answer to all questions, including the Fermi paradox. On the one hand, it is presumptuous to think that we have enough information to draw conclusions about the presence or absence of aliens. On the other hand, we cannot solve Earth's problems either. Therefore, it is important to focus on these issues now. Friends, dozens of spacecraft and hundreds of probes are leaving Earth and headed for our planet's twin sister, Venus. It is about the same size and about 80% of Earth's mass. Its temperature is too high for humans, and there is no air. But we went to Venus anyway, because scientists recently found traces of phosphine gas there, so there could be life there. After all, phosphine is produced by microbes and bacteria. So, humanity goes on a journey. The flight lasts from 3.5 to 6.5 months. But we finally made it there. Spaceships land on the planet. On its surface, people see heated deserts, lava lakes, and poisonous acid geysers. Scientists miscalculated. Phosphine never existed on Venus. We return to the rockets and prepare for a longer journey across the galaxy. Scientists believe there are at least 36 civilizations similar to our own in the Milky Way galaxy. They may be living organisms completely different from us. They may have different bodies and different eyes. They can talk and talk differently than we do. But an advanced civilization always has several characteristics: technological progress, and the use of advanced communication between individuals. Thus, these civilizations must be able to explore space, build cities, and communicate with each other as independent species. Let's look around our galaxy and find these civilized worlds. Thus, the Milky Way is a spiral of 100,000 lights. If a star explodes at one end in a supernova, the light from that event will not reach the other end until 100,000 years later. There are about 100 billion stars, and each of them may contain worlds similar to our own solar system. So, let's try to find them with the help of a giant fist. First, we look for iron-rich stars. They burn at the optimum temperature for life to grow. Iron in the interstellar system helps form the cores of the planets that will evolve into other civilizations. We are passing through the Milky Way, and there are many stars that fit the description, so we need another filter. Now let's find stars in this house that looks like the Sun. Such a star would have to be 100 times the mass of Earth and 333,000 times more massive. The age of the star is an important criterion. As it matures, it expands and becomes a red giant. At this time, it begins to absorb the surrounding planets. The life of such a star could end in a big explosion that would destroy everything around it. Therefore, the star we are looking for must be relatively young. Let's use our hands again. The stars are few, but the stars are many. Now let's focus on the planets. They must be in the star's habitable zone. Not very close, because then the temperature would be too high for life, but not too far away, or the planet will only live on ice. The planet's temperature should allow water to remain liquid. Another filter is the age of the candidate planet. It takes time for an advanced civilization to emerge. Based on Earth's experience, scientists estimate that it would take at least 4.5 billion years for life forms to develop to human levels. So we look for Earth-like planets, or giants. Using our ears one last time, voila, we have 36 worlds. Scientists published this study in April 2020. All that remains is to find these civilizations and make first contact with them. An advanced civilization can be detected by radio waves emitted from it. Let's say there is a planet A with primitive living organisms, millions of years of evolution, and they will become a civilization with advanced technology. Their method of communication will be through radio waves. Then the whole planet starts emitting radio waves when the star emits light. And here on Earth, we can receive the signal with antennas pointed into space. There is a problem with the interplanetary space. For example, Planet A is thousands of light years away from Earth. When it starts emitting radio waves, these signals will not reach us until 10 centuries later. We learned to emit and receive radio waves in 1895. If a civilization on Planet A were to emit a radio signal at the same time, we would not be able to receive that signal until 2895. It's the same on Planet A. In 1974, we sent a message into space in the form of a radio signal. And in that signal, we encoded our number system, human DNA, and information about the solar system. If there is an advanced civilization on Planet A, it will not be able to receive this signal until 2974. We will have to wait another millennium to get the answer. Another problem with radio waves is that they appear as flashes on the planet rather than as a constant glow. Radio waves are used only in a certain stage of civilization. That's usually where they start, then cell phones, cable TV, and the optical fiber era. And as technology advances, the radio wave background begins to fade. So it took about 100 years of using radio waves by civilization to find it. We once received a very strange radio signal of unknown origin. Its characteristics suggest that this signal was artificially generated, perhaps by an extraterrestrial civilization or a past starship. Further search for this signal has yielded no results, and this has given rise to many theories. It could be a signal from Earth reflecting off a satellite flying across the sky, or the trail of a comet several light years away. But let's face it, this is a civilization from deep space, probably one of only 36 that exist. Now, we need to contact them. We throw our luggage into the rocket and head for the suspected planet. Our rockets can travel 28,300 kilometers per hour. This means that a missile can cross the entire United States in 8 minutes. But even if an advanced civilization lived near our nearest star, Proxima Centauri, it would take about 73,000 years to reach it. Even traveling at the speed of light would take 4 years. So the problem of space travel needs to be solved first. Our scientists plan to achieve a quarter of the speed of light using lasers. Earth's powerful laser beam will guide the microscopic probe in the right direction. This probe will be able to reach our goal in about 17 years, and then another 4 years after the signal reaches Earth. We will find out if there is an advanced civilization. Another possibility for faster-than-light travel is a manned spaceship. He would squeeze the space in front of him and stretch his tail. Any point in the universe can be reached in seconds, but such travel is still a fantasy. Maybe one day we will be able to travel to different parts of the universe through worms. These are short passages that look like tunnels, but there is one problem. These worms may exist in black holes, the most mysterious objects in the universe. They are so heavy that even light cannot escape through them. Even our spaceships cannot withstand such a strain. Then there is the theory that the Earth is unique because it was created by chance. 4.5 billion years ago, our planet was a block of lava that began to cool and solidify. But his peace was shattered by an asteroid the size of a flying planet. The collision happened at such an angle that the Earth was not completely destroyed, but a part of the asteroid remained in our orbit. This celestial body near our planet stabilized the Earth's rotation, and the gravitational influence of the giant debris caused our core to heat up. In addition, the asteroid brought a lot of water to Earth. Such a collision is highly unlikely. It's like winning the lottery multiple times. Therefore, we have no reason to believe that life exists in space. However, there is no evidence that there are any advanced civilizations other than ours in the universe. The observable universe is home to truly astonishing large-scale structures that represent the breadth and depth of cosmic architecture. Among these giants are galaxy superclusters, large groups of galaxies that are gravitationally bound together. One of the most prominent superclusters is the Laniakea supercluster, which serves as our cosmic neighborhood. It contains approximately 100,000 galaxies and spans over 150 million light-years, representing the mind-boggling scale involved in our universe. In addition to superclusters, there are even larger formations known as cosmic filaments. These filaments consist of galaxies and dark matter, weaving complex patterns into the large-scale structure of the universe. The Sloan Great Wall is an important example of a cosmic filament, more than 100 million light-years long. Such large structures are interconnected to form a vast web architecture with empty spaces between them. This suggests that galaxies are not evenly distributed throughout the universe, but rather they form a complex region under the influence of gravity and dark matter. Even more impressive are the largest structures ever discovered, such as the Great Wall of Hercules Corona Borealis. This massive supercluster measures about 10 billion light-years across and is considered the most well-known structure in the observable universe. Its discovery complicates our understanding of cosmic evolution because it raises questions about how such large regions come together and what forces govern them. These massive structures provide important insights not only into the vast scale of space, but also into the fundamental processes that shape the universe over billions of years. As scientists continue to study them, they learn more about the basic fabric of matter, energy, and nature. The pursuit of knowledge about these great clusters piques our interest and our desire to understand our place in this grand cosmic scheme. Galaxy filaments and cosmic networks are the result of gravitational interactions and the complex dynamics of dark matter in the universe. These structures appeared in the early stages of cosmic evolution, after the Big Bang. As the universe cooled, matter began to clump together under the influence of gravity. Dark matter plays a key role in this process. It does not interact with light, making it invisible, but its gravitational pull has a significant effect on the distribution of galaxies. Over billions of years, regions with a slightly higher density of core matter began to attract more matter, forming the seeds of galaxies and clusters. As these local gravity wells deepened, they attracted more and more material from their surroundings. This created filaments, which are long structures that look like spaceships. These filaments connect large clusters of galaxies and form the web structure that fills the universe. As the universe continues to expand, the dynamics of matter evolves. Galaxies within the filaments are attracted to each other, eventually forming clusters at their intersections. This gravitational hierarchy is surrounded by high-density large voids that contain relatively few galaxies. The interplay of filaments provides the foundation upon which the universe is structured, displaying a beautifully orchestrated spatial arrangement. Computer simulations and observational data from telescopes are further enhancing our understanding of this phenomenon. These simulations show how dark matter affects the evolution of cosmic structure. Large-scale surveys, such as the Sloan Digital Sky Survey, allow astronomers to detect and map these large filaments, confirming theoretical models. Together, they reveal the dynamic processes that create the elegant cosmic web that spans our universe. Cosmic voids are the vast, empty spaces between galaxies and galaxy clusters that represent some of the larger structures in the universe. These voids can be tens to hundreds of millions of light-years across and are characterized by a lack of matter compared to denser regions. Although they appear to be devoid of galaxies, a closer inspection reveals that they are not entirely empty. They often contain faint galaxies, dark matter, and diffuse gas, albeit in much lower concentrations than their denser counterparts. The existence of these cosmic voids provides insight into the overall structure of the universe. The proliferation of voids and their surrounding filaments and clusters represent the web-like architecture of the universe, a phenomenon that reflects the influence of gravity over billions of years. Gaps are crucial to understanding cosmological evolution because they help scientists investigate the origin and nature of cosmic structure. By studying the vacuum, researchers can understand the changes in density that occurred in the early universe. Moreover, the properties of cosmic voids challenge our understanding of dark energy, the mysterious force that causes the universe to accelerate. The behavior of matter in and around voids can reveal valuable information about how dark energy affects the expansion of space. For example, observing how galaxies move in and around voids can provide information about the distribution of mass in the universe and help us understand cosmic dynamics. The study of cosmic voids also raises interesting questions about the fundamental nature of the universe. They serve as testing grounds for cosmological models, allowing researchers to assess the validity of theories such as the Standard Model of cosmology. As science advances and observational techniques improve, space probes continue to unravel the mysteries of the universe, enhancing our understanding of the governorship of cosmic evolution. Dark matter plays an important role in the formation and evolution of cosmic structures throughout the universe. Although invisible, neither emitting nor absorbing light, dark matter makes up about 27% of the total mass-energy content of the universe. Its gravitational influence is key to understanding how galaxies, clusters, and even larger structures such as superclusters and cosmic filaments are formed and maintained. In the early universe, after the Big Bang, matter began to clump together under the force of gravity. Although the normal matter that emits light and forms stars and galaxies begins to accumulate, it is dark matter that does not appear to form the basis of this cluster. Dark matter does not interact electromagnetically, meaning it does not collide with matter to dissipate energy. This property allows it to remain gravitationally bound and form massive halos surrounding galaxies and clusters. These halos act as gravitational wells, attracting ordinary matter and helping the formation of stars, galaxies, and larger structures. The processes of cosmic evolution and structure formation are closely related to the behavior of dark matter. When galaxies merge or interact, their dark matter can also collide and merge, which can lead to the growth of large galaxies and galaxy clusters. Understanding the dynamics of dark matter interactions helps scientists explain phenomena such as the rotation curves of galaxies. These curves show that stars orbiting outside galaxies are moving faster than expected based on visible matter. This suggests that there is additional invisible mass associated with dark matter. Astronomical observations and simulations of large-scale structures shed more light on the role of dark matter. By mapping the distribution of galaxies and clusters, researchers can map the corresponding distribution of dark matter. Projects such as gravitational lensing provide direct evidence of the existence and distribution of dark matter throughout the universe by measuring how light from distant objects is bent by massive structures. As researchers continue to explore the nature of dark matter, they enhance our understanding of its profound effects on the cosmic landscape and the structure of our universe. Beyond our observable universe lies a tantalizing and enigmatic realm. Although we can analyze the structures in the cosmic environment, understanding the nature of these cosmic structures is influenced by many different cosmological theories. One common idea is that the conditions surrounding these structures may vary, resulting in different formations. For example, while our universe exhibits a specific distribution of galaxies, clusters, and voids, other regions may vary in density and order, resulting in different large-scale structures. One hypothesis suggests that physical laws may differ in different regions of the universe. If fundamental constants such as gravity or the speed of light differ from our observable horizon, the evolution of cosmic structures in these regions may produce results that differ dramatically from what we witness nearby. Such changes could lead to exotic astrophysical entities or entirely new celestial shapes that defy our current understanding of physics. In addition to potential changes in physical laws, the overall geometry of spacetime is a critical factor influencing the structure of the universe. Measurements of the cosmic microwave background radiation suggest that the observable universe appears to be flat. However, if the universe is truly infinite and far beyond what we can observe, it could introduce various curvature features that could affect the development of large-scale cosmic structures. The concept of the multiverse also comes into play, where our universe is potentially one of countless others, each with its own unique physical properties and structural formation processes. In such a scenario, some universes may adopt strange structures or even strange rules governing their cosmic evolution. While these ideas remain speculative, they drive the imaginations of scientists and theorists, furthering the exploration of the mysteries of the universe. Attempting to understand these hypothetical cosmic realms beyond the visible universe deepens our uncertainty. Dark matter is a mysterious, non-luminous component of the universe that does not emit, absorb, or reflect light, making it invisible to conventional observational techniques. Dark matter is thought to make up about 27% of the mass energy of the universe. Scientists estimate its existence based on its effects on visible matter, radiation, and the overall structure of the universe. One of the strongest lines of evidence for dark matter comes from observations of galaxy rotation curves. When astronomers measure the speed of stars orbiting in the outer regions of galaxies, these stars move much faster than expected based on the gravitational effects of visible matter such as stars and gas. According to Newtonian physics, they should show a decreasing velocity as they move away from the galactic center. However, the observed velocity remains constant, indicating that the galactic halo contains more mass than can be accounted for by stars and gas alone, possibly in the form of dark matter. Another important piece of evidence comes from gravitational lensing, the phenomenon in which light from distant galaxies is bent by the gravitational pull of large foregrounds such as galaxy clusters. Observations show that the amount of bending goes beyond that which depends only on the apparent mass. This inconsistency suggests that there is additional invisible mass that exhibits gravitational pull, consistent with the presence of dark matter. Moreover, the distribution of galaxies in the universe follows a web structure under the influence of dark matter. Cosmic structure formation simulations involving dark matter agree closely with observations of the large-scale structure of the universe, such as galaxy clusters and voids. These models suggest that dark matter acts as clusters of visible matter that guide the formation of galaxies and other cosmic structures. The exact nature of dark matter remains a deep mystery, and various candidates have been proposed, such as non-massive particles. Research is ongoing, using cutting-edge technologies and experiments aimed at directly or indirectly detecting dark matter. The search for dark matter is important because it not only holds the key to understanding the composition of the universe, but also informs the fundamental laws that govern the cosmos. Dark matter has a profound effect on galaxy formation and the overall architecture of the universe. Its gravitational properties are important in shaping the large-scale structure we observe in the universe today. In the early universe, shortly after the Big Bang, dark matter began to clump together, forming massive halos that provided a gravitational field within which ordinary matter could gather. This high concentration of dark matter created gravity wells that attracted gas, dust, and other simple matter, facilitating the birth of galaxies. As galaxies form, their dark matter plays an important role in determining their size, mass, and rotation speed. Dark matter helps maintain the stability of galaxies by providing additional gravitational pull only with visible matter. This stability is particularly important because the forces at play during galaxy formation are enormous, and the gravitational pull of dark matter allows complex structures to form that do not collapse under their own dynamics. When galaxies interact or merge, the dynamics of their dark matter has a significant impact on the outcome of these events. For example, during a merger between two galaxies, their dark matter halos can collide and merge with visible matter. This interaction can lead to the formation of larger galaxies, which often exhibit different properties compared to smaller ones. This merger process is a critical aspect of galaxy evolution, contributing to the development of cosmic structures throughout the universe. On a larger scale, dark matter represents the overall distribution and motion of galaxies. The gravitational influence of dark matter creates the structure of the cosmic web, where galaxies and clusters form along filaments and nodes with large gaps between them. This gravitational network shows how dark matter organizes space and affects the motion of galaxies over time, shaping the dynamic behavior of galaxies and clusters as they move through the evolving universe. Dark matter is more than just a facilitator of cosmic evolution. It serves as the primary force driving the formation and construction of galaxies and the larger cosmos. The search for dark matter particles has led scientists to propose several interesting candidates, each from a different theoretical background in particle physics and cosmology. One of the most widely studied candidates is the weakly interacting massive particle, often abbreviated as WIMP. WIMPs are predicted to have masses on the order of hundreds of GeV or giga-electron volts and interact with the weak nuclear force and gravity. The theory postulates that they were produced in large quantities in the early moments after the Big Bang. Direct detection of WIMPs will be difficult due to their weak interactions, but some experiments aim to observe scattering events with potential matter. Another promising category of dark matter candidates is the hypothetical elementary particle proposed to solve problems related to quantum chromodynamics. Particles are light, slow-moving particles that can make up a large portion of dark matter. They will interact very weakly with other particles, effectively repelling them. Researchers are exploring the potential for detecting axons through experiments that look for them to convert into photons when exposed to strong magnetic fields. There are also supersymmetric particles, which arise from theories that extend the standard model of particle physics. In these models, each elementary particle has different properties. Candidates from supersymmetry, such as neutralinos, have the necessary properties to account for dark matter. Their stability and interactions governed by the weak force make them strong candidates in some theoretical frameworks. Finally, supermassive black holes provide an alternative explanation for dark matter. These would arise from changes in density in the larger universe, potentially accounting for the effects of dark matter through gravitational interactions. Although this theory differs from ordinary particle candidates, it remains a point of active research given the complexity of cosmological evolution. These candidates bring together the various approaches taken to solve the dark matter enigma. Ongoing experiments are designed to detect or rule out these possibilities, improving our understanding not only of dark matter, but of the fundamental physics of the universe. Each approach promises to advance scientific knowledge and may lead to profound discoveries about the composition of the universe and the laws that govern it. Dark energy is an enigmatic form of energy that permeates all of space and is responsible for the observed acceleration of the universe. Dark energy, which accounts for about 73% of the total mass energy content of the universe, has puzzled scientists since its discovery. Unlike ordinary matter and dark matter, which are gravitationally attracted, dark energy exerts a repulsive force, causing galaxies to accelerate apart from each other. Traces of dark energy were first discovered in the late 20th century, primarily through observations of distant supernovae. In the mid-1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the luminosity of JA supernovae, which serve as a reliable standard candle for determining cosmic distances. By observing these supernovae, teams would discover that the universe's expansion is slowing due to gravity. However, their data showed a surprising result. The supernova appeared darker than expected, indicating that they were farther away than previously thought. This led researchers to conclude that the expansion of the universe is accelerating rather than slowing down. The key to understanding this acceleration lies in the concept of dark energy. To explain the observations, scientists introduced dark energy as the driving force behind the accelerated expansion. Various theoretical frameworks have been proposed to describe dark energy, one of the most famous models of the cosmological constant. The cosmological constant, proposed by Albert Einstein at the beginning of the 20th century, simultaneously complements the energy density. This reflects the idea that as the universe expands, the energy density remains constant. Other theories have emerged, including quintessence, which suggests that the density of dark energy may change over time. Despite these various models, the true nature of dark energy remains elusive. Observations of the cosmic microwave background, the large-scale structure of the universe, and other astrophysical phenomena have helped improve our understanding of dark energy. Ongoing research continues to investigate this mysterious substance, as unraveling its nature could shed light on fundamental aspects of the universe and the ultimate fate of cosmic evolution. Dark energy plays an important role in the future of the universe, primarily because of its role in the accelerated expansion observed over the past few billion years. As dark energy continues to exert its influence, it shapes potential scenarios for the ultimate fate of the universe. The exact nature of dark energy remains an open question, but its consistency suggests several futures for the universe. Big Freeze Scenario. In this model, as the universe expands at a rate controlled by dark energy, galaxies gradually fade away from our observable horizon. Over large timescales, star formation will slow down, leading to an increasingly cold and dark growing universe. Existing stars will run out of nuclear fuel, and without new stars forming, most of the matter will remain in the form of black holes and white dwarfs. Eventually, the universe will reach a state of thermodynamic equilibrium, characterized by a uniform temperature near absolute zero, rendering it a desert and inert space. Another scenario is a Big Rip, where the influence of dark energy increases, causing the escape to expand. In this model, the accelerated expansion can be so pronounced that it eventually separates galaxies, stars, and even atoms. If the energy density of dark energy increases without limit, all large-scale structures will collapse, ultimately leading to a catastrophic end to the universe. At the other end of the spectrum, some theories suggest that dark energy could evolve over time, perhaps leading to a steady state or even transitioning to gravitational forces. This change could reverse the current acceleration of cosmic expansion, allowing galaxies to merge and form larger structures, leading to a cyclical pattern of cosmic evolution. As researchers gather more information from observations of supernovae, the cosmic microwave background radiation, and galactic scattering, They aim to improve our understanding of dark energy and its effects on the universe. Each of these potential destinies points to the complex relationship between dark energy and the cosmos, revealing how this mysterious force can ultimately shape evolution and the fate of everything within it. The evidence for the expansion of the universe is strong and multifaceted, contributing to our understanding of cosmological dynamics. One of the earliest and most compelling evidences comes from observations of galaxies and their redshifts, recognized by Edwin Hubble in the late 1920s. Hubble noted that distant galaxies are moving away from us, and the light they emit shows a shift to the red end of the spectrum. This red shift indicates that the wavelengths of light are stretched as galaxies shrink, a phenomenon consistent with the Doppler effect. Hubble formulated his law, which states that the farther away a galaxy is, the faster it is moving away and the universe is expanding. In addition, the cosmic microwave background rays, the glow left over from the Big Bang, provide further support for this expansion. Discovered in the 1960s, this relic radiation is remarkably uniform, but there are small variations that reveal information about the density and temperature of the universe. Measurements from satellites, such as the Wilkinson Microwave Anisotropic Probe and the Planck mission, show these changes with great precision. According to the data, the universe has been expanding since its creation, and the cosmic microwave background serves as a snapshot of the universe as it was around 300,000 years ago, after it cooled enough to form atoms. Supernovae also contribute to the evidence for the universal expansion, particularly type Ia supernovae, which serve as reliable standard candles for measuring astronomical distances. Observations at the end of the 20th century showed that these supernovae were less luminous than expected, suggesting that they were far away due to the acceleration of the universe's expansion. This discovery was instrumental in proving not only the expansion of the universe, but the expansion rate is increasing due to dark energy. Finally, the large-scale structure of the universe, including the distribution of galaxies and cosmic filaments, provides additional evidence for expansion. Current observations show that galaxies are not uniformly distributed. Instead, they form a large cosmic web structure that interacts with gravity. This distribution is a direct result of the expansion history of the universe, further reinforcing the paradigm of a dynamically evolving cosmos under the influence of forces at play since the Big Bang. Together, this evidence creates a powerful picture of an ever-expanding universe, with each piece contributing to our understanding of its origins and evolution over time. The Hubble constant is a key parameter that describes the rate at which the universe is expanding. It shows the relationship between a galaxy's distance and its rate of recession, providing a measure of how quickly galaxies are moving away from us as the universe expands. The Hubble constant is usually expressed in megaparsecs per kilometer per second, meaning that for every additional megaparsec, the galaxy is receding by a certain number per second. Edwin Hubble's discovery of this relationship in the late 1920s fundamentally changed our understanding of the universe. His observations showed that galaxies farther from Earth are receding at a greater rate, indicating that the universe itself is expanding in one direction. This expansion can be thought of as the stretching of space, with the galaxies embedded in that space dissipating over time. Understanding the Hubble constant is critical to determining the size and age of the universe. By measuring the recession velocities of different galaxies and their distances using methods such as standard candlestick or redshift measurements, astronomers can calculate the Hubble constant. This measurement allows scientists to estimate how long the universe has been expanding since the Big Bang, yielding its age, which is currently about 13.8 billion years. However, it should be noted that measurements of the Hubble constant yielded slightly different values depending on the methods used. Planck satellite observations measuring the cosmic microwave background radiation suggest a certain value for the Hubble constant, while measurements from large surveys of supernovae and galaxy distributions provide larger values. This discrepancy has led to debate and research in the field of cosmology, as scientists seek to reconcile these differences and better understand the underlying physics of the universe's expansion. Ultimately, Hubble serves as an important bridge connecting observations of constant recession velocities and distances, strengthening its role in understanding the expanding universe and guiding future investigations into its fate. Cosmic acceleration refers to the observed expansion of the universe over the past few billion years. This continuum behavior indicates that the galaxies are moving away from each other at increasing speeds rather than slowing down, as would be expected from gravitational acceleration. The discovery of cosmic acceleration changed our understanding of the dynamics of the universe and had important implications for cosmology. The main explanation for cosmic acceleration is dark energy, a mysterious form of energy that permeates space and resists gravity. Dark energy is thought to make up 73% of the total energy density of the universe. Unlike ordinary matter, which has a gravitational pull, dark energy appears to be a repulsive effect pulling galaxies apart. The nature of dark energy remains one of the most profound enigmas of modern astrophysics, with various theories proposed to describe its properties, including the cosmological constant, which is a constant energy density. Observations supporting cosmic acceleration come primarily from studies of distant supernovae, particularly type Ia supernovae. These supernovae serve as reliable distance indicators, allowing astronomers to measure the expansion history of the universe. When the researchers found that these supernovae were weaker than expected, it showed that they were farther away than previously thought, leading to the conclusion that the expansion of the universe is accelerating rather than accelerating. Another piece of evidence for cosmic acceleration is observations of the cosmic microwave background radiation and large-scale structure. Measurements of changes in the cosmic microwave background after the Big Bang provide insight into the density and composition of the early universe. The subsequent spread of galaxies and galaxy clusters through space is consistent with an accelerated expansion scenario, as structures formed from density fluctuations are influenced by dark energy. Despite extensive research on dark energy and cosmic acceleration, questions remain about its true nature and behavior. Ongoing experiments and observational campaigns aim to improve our understanding, potentially revealing physics and changing our understanding of the evolution and fate of the universe. The implications of cosmic acceleration and dark energy are not only interesting, but also delve into deeper questions about the very fabric of reality. The expansion of the universe is of great importance not only for the regions we can observe, but also for the regions beyond the observable limits. As the universe expands, it affects the dynamics and distribution of matter on large scales, and this expansion drives the evolution of cosmic structures both within our observable universe and in regions beyond it. One of the main effects of this expansion is the notion that the regions beyond our observable universe may be shrinking away from us at speeds exceeding the speed of light due to the metric expansion of space. This means that light from galaxies in these distant regions can never reach us, remaining forever beyond our cosmic horizon. As the universe continues to expand, many of these regions will move away from our observables, leading into the future, when the night sky will slowly empty of distant galaxies. This eventual isolation can lead to a universe that appears dark and desolate, changing our perception of space over cosmological timescales. Magnification effects raise interesting questions about the potential existence of structures beyond our observable universe. While we cannot directly observe these regions, theoretical models suggest that they may contain galaxies, clusters, and cosmic filaments similar to our observable limits. However, these structures evolve differently depending on local conditions, gravitational interactions, and dark energy distribution. Such changes may mean that the universe we see is not just an extension of what we can observe, but may offer unique features. In addition, the rate of expansion can affect the fate of the universe. If the properties of the dark model change, as some models suggest, this could lead to very different cosmic scenarios in the observable and unobservable regions of the universe. For example, if dark energy becomes stronger, it could lead to big rip-like scenarios where cosmic structures are disrupted, even affecting the integrity of the farthest reaches of space. Ultimately, as scientists continue to study the fundamental laws governing the expansion of the universe, our understanding of its consequences will be near and far. Uncharted regions of the universe may hold secrets that defy our understanding and help us understand the fabric of reality, even if we never see it with our own eyes. The ultimate fate of the universe is a topic of great intrigue among cosmologists, with prevailing theories suggesting several potential scenarios based on the expansion of the universe and the nature of dark energy. As the universe continues to expand, it will push galaxies further apart. This expansion, driven by dark energy, is accelerating over time, leading to the possibility of a superfreeze. In this scenario, the universe becomes increasingly cold and desolate. Stars run out of fuel and galaxies recede until they fall into obscurity. Alternatively, some models predict a major collision. In this scenario, if the universe is dense enough, gravity can eventually stop expanding. The universe would then collapse back under its own gravity, potentially creating a singular state similar to the conditions at the beginning of the universe. This collapse could return all matter to an infinitely dense point, possibly leading to another Big Bang and the birth of a new universe. Another interesting possibility is the Great Rip. This theory suggests that if dark energy becomes stronger, it can tear apart galaxies, stars, planets, and even atoms. In this case, the fabric of the universe would eventually rupture, causing all structures to collapse violently. Finally, there is the concept of a steady-state universe, in which the expansion continues indefinitely, but the universe does not change over time, filled with new matter continuously created to fill the voids left by the expanding universe. These theories highlight the complexity and uncertainty surrounding the fate of our universe, calling for further exploration and research in the field of cosmology.
The solar system is just a speck of dust against the backdrop of giant galaxies and star clusters. There are thousands of stars within 100 light-years of it. Some of them are barely visible against the cosmic abyss. Others shine so brightly that they can even be seen from other galaxies. There are also many invisible objects hidden in the depths of space, from massive brown dwarfs to rocky exoplanets comparable to Earth. Some of them can awaken the spirit, while others are threatening. But all this diversity pales in the scale of the galaxy. At least 200 billion stars and more than 1 trillion planets are hidden in its depths. Such a number of unique space objects cannot be fully explored. So let's talk about the closest ones. By galactic standards, the region of space adjacent to the solar system is considered lightly saturated with both luminaries and other cosmic objects. However, about 50 star systems within 15 light-years of Earth are already known. Some of them are individual bulbs. Others contain 2 or more components, so the total number of stars in this region is 65. Many of them have exoplanets and protoplanetary disks of gas and dust where the process of formation of celestial bodies continues. To explore all this diversity, we need to create a map of our immediate surroundings. Gradually leaving our home planet, we cross dozens of light-years into the cosmic void and visit many distant worlds. It's time to head for the stars. 6 light-years from the Sun, we reach our first target, the small red dwarf GJ 699, also known as Barnard's star. It is remarkable because it moves across the sky at an incredible speed and can cross the lunar disk in 180 years. This is due not only to the short distance to the target, but also to the very fast proper motion of the star. The flying Barnard is approaching the solar system at just over 100 kilometers per second, and in about 10,000 years, it will be the closest star to us. So far, the distance between it and the Sun is only 3.8 light-years. But even at this distance, the faint glow of the red dwarf is not enough to be seen without optical instruments. The mass of the star is only 17% of the solar mass, and its radius is about 6 times smaller. Like all red dwarfs, the flying Barnard is pretty cool. Its surface temperature is only 3,134 Kelvin, just below 2,900 degrees Celsius. According to this information, it is not surprising that the luminosity of the object is 2,300 times smaller than our star. In 2018, the results of a 20-year observation of the star's own motion were published, which could provide evidence for the existence of a nearby exoplanet. Available calculations indicate that it is a cold super-Earth with a mass of at least 3.2 Earth masses. The planet, dubbed GJ 699b, is located about 0.4 AU from the center of the system and completes a full revolution around its parent star in 233 days. Unfortunately, the exoplanet's orbit is located so that it does not pass between Earth and its parent star. Therefore, it is almost impossible to perform a spectral analysis of the target. However, mathematical modeling may give us clues. Because Barnard's star is so dim, its planetary companion receives 50 times less energy from the Sun than Earth. That is why the surface temperature of the celestial body is very low, only 105 Kelvin, or minus 168 degrees Celsius. However, it cannot be ruled out that tidal disturbances or radioactive decay have released enough energy in the planet's interior to form a warm underground ocean. If this is true, potential life in its depths has had plenty of time to slowly evolve. Indeed, among known luminaries, Barnard's star is probably one of the oldest. It is estimated to be more than 10 billion years old, which is only a few % of the expected lifespan of a star. Barnard's star is one of the most important targets of possible interstellar missions because of its proximity and favorable direction of motion. Only time will tell if an artificial spacecraft will ever be able to reach it. Meanwhile, on the other side of the Sun is almost the exact opposite, a dim red dwarf. We are talking, of course, about Sirius, the brightest star in the night sky, located 8.6 light-years from our planet. On Earth, this bulb looks like a single light source. However, a closer look reveals that it is not a single object, but a double star. Currently, the two parts of the system are at their greatest distance from each other, about 30 AU. The main luminary, also called Sirius A, is a bright blue-white star with twice the mass of the Sun. In addition, its diameter is 70% larger than that of the Sun, and its surface temperature reaches 10,000 Kelvin. This allows Sirius A to emit 25 times more energy than our star. The second object, known as Sirius B, is barely visible against its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to the solar mass. Like all stars of this type, its surface temperature is very high, reaching 25,000 Kelvin. However, because of its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After a long and persistent study, no signs of planets have been found in the vicinity of Sirius. The reason for this may be either the young age of the star system or the special position of the ecliptic plane. Consequently, hypothetical exoplanets do not travel between the light source and Earth, so they cannot be detected by the transit method. Another hypothesis states that about 120 million years ago, Sirius B ran out of stellar fuel and became a red giant. Shortly thereafter, it shed its outer shell and transformed into a compact and extremely hot white dwarf. The resulting explosion destroyed the protoplanetary disk of gas and dust that surrounded the young star system at the time. Its remains are scattered in the surrounding space, leaving the ascending planets a chance to survive. Currently, both parts of the system move around a single center of mass in moderately elongated orbits, making a complete revolution every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance to it is about 7.5 light-years, after which the system begins to slowly drift away from us. This situation will continue for another 660 million years, after which Sirius A will suffer the same fate as its companion. In a short time, a powerful flare increases its luminosity 1,000-fold, but in a few months, the star will completely fade away and disappear from the sky forever. Leaving the vicinity of Sirius, full of destructive ultraviolet radiation and stellar winds, we will travel close to the solar system to reach a small star 14 light-years from Earth. It is known in several catalogs under different names, one of which is Wolf 1061. The luminary is a red dwarf with a radius about 30% of the Sun. Its mass is about 4 times smaller than our star, and its surface temperature is 3,272 Kelvin, or about 3,000 degrees Celsius. Like all objects in this class, Wolf 1061 is extremely obscure. Its luminosity is only 0.14% of the solar luminosity, so the star cannot be seen with the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments in our nearest star system. At least 3 exoplanets have been discovered in its vicinity, all of which are rocky and similar in composition to Earth. In addition, the conditions of all 3 celestial bodies differ significantly. The first and closest exoplanet to its parent star is called Lupo 1061b. It is located at a distance of 0.038 AU from the center of the system and makes a complete revolution around it in about 5 days. The mass of the object ranges from 1.5 to 2 Earth masses, and the radius it is 20% larger than the corresponding parameter of our planet. The celestial body is believed to be tidally locked and is constantly on the same side of the star. So the temperature on the day side of the object is very high, and the rockets and stellar winds of a nearby star virtually preclude the existence of an atmosphere. All these factors make the exoplanet completely unsuitable for the formation and maintenance of life. The second object in the system, Wolf 1061c, is located at a distance of 0 to 0.089 AU from the star, and makes a complete revolution around it in about 18 days. Thus, it is in the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 4 times more massive than our planet and is categorized as a super-Earth. Observations show that its radius is about 1.6 times larger than Earth's, and the gravity of Earth's surface is calculated to be 60% greater than what we are used to. An exoplanet receives much less energy from its star than Earth receives from the Sun, so its equilibrium temperature is much lower. It is 223 Kelvin, or about minus 50 degrees Celsius, which is slightly warmer than Mars. However, due to daily and seasonal temperature fluctuations, liquid water may be present on the surface of the celestial body. In a dense atmosphere with a strong greenhouse effect, this probability is even higher, and conditions on the planet may approach comfortable. Of all the currently known potentially habitable exoplanets, Wolf 1061c is one of the closest and ranks 5th on the list. The third object in the system is known as Wolf 1061d. It moves in a remarkably elongated orbit. At its farthest point, the distance between the planet and its parent star reaches 0.73 AU. The perihelion of the orbit is much closer to the center of the system, only 0.21 AU. At the same time, the annual cycle of the celestial body lasts about 217 Earth days. Wolf 1061d is calculated to have a mass of about 7.7 Earth masses. If this celestial body is a rocky object, its radius will be about 1.7 terradius. If the planet is a mini Neptune with a thick multi-layered atmosphere, its diameter should be at least 2.2 times the diameter of our planet. Despite the relatively high eccentricity of its orbit, Wolf 1061d will never reach the habitable zone of its star. This system is one of the main targets of future research, so new discoveries are likely to be made soon. The star Lupo 1061 is known, among other things, for being located almost at the edge of the so-called local interstellar cloud. This is a region of space filled with hot but extremely rare hydrogen. Its temperature is about 7,000 Kelvin and only 0.3 atoms per cubic centimeter of space. It is about half the average size of the Milky Way. Over the past 10,000 years, the solar system has been moving through the local cloud. Its average diameter is about 30 light-years, but our system is almost at its edge. Alpha Centauri, for example, is already in the nearby so-called G-cloud. We spend another 2,000 years in our cloud, A, after which we enter even rarer and hotter territory. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has its own momentum directed perpendicular to the direction of motion of the solar system, as well as a magnetic field and radiation. Despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to Earth's organisms. The solar wind shields us safely from the cosmic hydrogen, and the Earth's dense atmosphere absorbs the effects of those particles still breaking through the heliosphere. However, traces of the isotope iron-60, also called interstellar, have been found in Antarctic ice. It is said to have been brought to Earth from a local interstellar cloud. Continuing our journey through outer space, we soon discover a rather unusual star called AP Dove, located 27.4 light-years from Earth, at a time when the dinosaurs were extinct on our planet. Even more surprisingly, the event occurred in a completely different region of the galaxy, 450 light-years away from the object's current location. Usually, young stars stay near their stellar cradle for quite a long time, up to several 100 million years. Analyzing AP Dove's proper motion shows that it was probably once part of the scattered cluster IC 2391. It contains about 30 stars that share a common origin and direction. But a few million years ago, one of them exploded, upsetting the delicate balance of many cosmic bodies. Being a very small red dwarf with a mass only 13% of the Sun, this star emits 4 times more energy than any other known celestial body with the same parameters. In addition, its radius is 2 times larger than the value calculated by the current theory of stellar structure. Strangely enough, finding answers to these riddles helped us to find another unusual feature of the star. Indeed, according to a spectral analysis of its radiation, the stellar matter of the AP Dove contains an extraordinary amount of lithium. Usually, this element is abundant in protostars, but it burns up quickly once fusion begins. This means that it is a very young star, not yet in the Premier League. Consequently, AP Doves is characterized by instability and explosiveness. It undergoes strong flares and ejections of stellar matter, during which its brightness can increase tenfold for an instant. However, observations show that there are no large cosmic objects within 4.5 AU of this star. Apparently, its age is too young to form full-sized planets. However, it is a unique cosmic body that is very important for understanding the process of early stellar evolution. As we've seen, not all stars have planetary systems, so our next stop is the orange dwarf Gliese 370, located 37 light-years from Earth. In 2011, the exoplanet Gliese 370b was discovered nearby. The object was found using the radial velocity method, and its mass is 4 Earth masses. Under these conditions, the gravity on its surface must exceed our normal gravity by at least 40%. Gliese 370b is located at a distance of 0.26 AU from its parent star and completes a full annual revolution in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the value of albedo and its surface is close to the Earth's value, the average temperature of the celestial body should be approximately 25 degrees, which is a few degrees higher than on Earth. The fact that the exoplanet is located far enough away from its parent star suggests that it is not in a tidal grip and has its own diurnal cycle. This contributes to a more even distribution of heat on the surface of the celestial body, and, as a consequence, may cause a milder climate. The moderately high gravity should smooth out the planet's topography, which, combined with the abundance of liquid water, could cause the formation of spacious seas that are warm and shallow. Such places are traditionally considered the most convenient for the creation and preservation of life. At the time of its discovery, Gliese 370b was considered one of the most attractive exoplanets for possible biological life. However, subsequent research suggests that conditions on its surface are a bit more uncomfortable than previously thought. In particular, it is possible that the atmosphere of the celestial body is too dense and has a strong greenhouse effect. However, even according to the most pessimistic predictions, the average surface temperature of the object does not exceed 78 degrees Celsius, which corresponds to a temperature difference of about 100 degrees. Given that our planet's climate was about the same during the Archean, Gliese 370b remains a very attractive exoplanet for the search for extraterrestrial life. This means that its research continues. If we stop for a moment and look around, we realize that we are already more than 50 light-years away from the solar system. There are more than 1,000 stars in this radius, most of them single stars. Other objects are twins, or even represent entire constellations. The most obvious example of this is Custer, a complex, amazing system with 6 components at once. This star system is located 50 light-years away from Earth and is visible to the naked eye as a single light source. As the second brightest object in the constellation Gemini, and the 23rd object in the entire starry sky, Custer has been known to man since ancient times. Since the system has up to 6 components, its structure is quite complex. The 2 brightest of them, Castor A and B, are blue-white luminaries similar to Sirius, each with a neighboring red dwarf. The distance between the centers of mass of these twin stars is approximately 110 AU, and a complete revolution takes 445 years. About 600 AU from wheels A and B is another close double system consisting of a pair of very similar red dwarfs. Both stars have a mass of about 0.6 C and a surface temperature of about 3,900 K. The 2 stars are so close to each other that their rotation takes less than 20 hours. They move around the common center of mass of the entire system in a very elongated elliptical orbit with an orbital period of about 14,000 years. No confirmed exoplanets have yet been found in the Custer system. However, if there are any, they are most likely to be found here, near the faintest component of the system. For example, in 2018, astronomers discovered changes in the orbital period of Custer C that suggest there may be a brown dwarf about 49 times more massive than Jupiter nearby. It is calculated to be 14 AU away from its parent star and completes a full revolution around it in 54 years. It is quite possible that, like many red dwarfs, C of Custer has rocky exoplanets near its star. In this case, the view from the sky of such a hypothetical point must be truly incredible. On one side, much of it is illuminated by 2 continuously rotating crimson lights in the sky, and on the other side, the light from hundreds of stars breaks the eternal darkness. Times brighter than Earth's moon. Really? I can't verify it yet. Although the lights we visited are separated by vast distances, they are all part of a single structure with a total length of about 300 light-years. Called the local bubble, it contains not only thousands of stars, but also several large structures, including the local interstellar cloud. The local bubble was formed by the successive explosions of several supernovae that occurred between 10 and 15 million years ago. It's a giant cloud of interstellar gas, heated to 1,000,000 Kelvin. Because of its high temperature, the gas tends to expand, making it about 10 times less dense than the galactic average. In addition, hot ionized hydrogen continuously emits X-rays. However, the magnetic fields of the Sun and Earth and the planet's atmosphere successfully protect us from harmful radiation. The local bubble is confined to other similar settings. For example, the so-called Bubble 1, formed by supernova explosions near Antares, is somewhat out of the solar system's path. This giant cosmic structure interacts with our bubble for a long time, causing huge condensations in the bordering region. The center of the neighboring bubble is about 500 light-years away from us, and in a few tens of millions of years, the solar system will reach its edge, hot gas clouds and scattered clusters, giant nebulae and star streams. All these majestic cosmic structures form single systems called galaxies. These, in turn, merge into galactic filaments, giant streams and walls, billions of light-years long. Thus is formed the large-scale structure of the universe, hiding in its depths countless different lights and worlds. Who knows what we'll find in them?
Mars. An attentive observer looking at the starry sky will see a small reddish round spot. This is Mars. This object attracts attention with its mystery and constant hope to find the very thread that will reveal the great mysteries of the universe. The parameters of the planet. The first known observations of celestial neighbors were made during the time of the pharaohs in Egypt, 1,000 and 1,500 years before Christ, to determine the planet's position in the sky between Earth, the asteroid belt, and Jupiter. Mars is one of the planets in the solar system, located in the fourth orbit after Earth. Mars revolves around the Sun in an elliptical orbit with a very significant eccentricity of 0.934. Therefore, the distance between them during the revolution has changed by 42.6 million kilometers. These celestial bodies are either approaching each other or moving away from each other. Chemical composition: jacket, 21% silicon, 12.7% iron, 3.1% sulfur. The jacket is impregnated with iron sulfide. The iron content of the metal is low. The core is composed mainly of iron and sulfur. Orbit and rotation: the planet revolves around the Sun in an elongated elliptical orbit at a speed of 24 kilometers per second. Consequently, the distance between them is 206.6 to 249.2 million kilometers. The rotation period is 687 Earth days or 188 years. The Martian day is a solid 37.5 to 40 minutes longer than ours. The planet owes these orbital parameters to the gravitational forces of its cosmic neighbors. According to scientists, Mars used to have a more circular orbit, perhaps even less eccentric than Earth's orbit. Mars' axis is tilted 25.9 to 25.19 degrees, so the seasons alternate, although their duration varies. Interesting fact: blizzards rage on Mars at night. Wind gusts pick up falling snowflakes, causing real storms. Temperature on Mars: due to the lack of a suitable atmosphere, the surface of the planet, which is close to Earth at the point of exit from the solar system and therefore less heated, is very cold. The average annual temperature is -50 to -60 C. There are facts of warming of the poles and equator to +35 C, but this does not change the overall meteorological picture. Atmosphere: since our cosmic neighbor is a potential host for life, scientists have carefully studied its atmosphere. A lot of interesting things have come to light, but, as is often the case in science, many optimistic predictions had to be abandoned. And here's why. The planet's atmosphere is very rare, to 1% of the Earth's atmospheric pressure. On our planet, to reach the conditions of Mars due to the strong influence of the gas-air column, it is necessary to rise to 35 kilometers. The gas shell of Mars is 95% carbon dioxide, but because of its thinness on the planet is not observed greenhouse effect. But there is water, though not in a liquid state. Giant polar caps of H2O saturate the air with water vapor. Scientists are confident that they will find seas inside the planet. It may even be low. Interestingly, the thin layer of the Martian atmosphere completely determines the climatic conditions on Earth. Winds blow there too, dust storms blow through fog, and terrible cold, sometimes up to 150 degrees. Expiration of the atmosphere: until recently, the main hypothesis about the expiration of the atmosphere from the surface of the red planet was the unproven fact of collision with a cosmic body. Time has made adjustments. In 2013, the interplanetary station MAVEN explored Mars. Much has become clear from the study. Billions of years ago, the planet was hot and humid. There were bodies of water that could easily have been the habitat of living things. 4.2 billion years ago, Mars lost its magnetic field for unknown reasons. The atmosphere leaked out into space. It's still happening today, but at a much lower rate of 100 grams per second. During solar storms, the process of losing the gas layer is greatly enhanced by solar wind streams. If there is no change, our neighbor's atmosphere will disappear into space in a few billion years. The surface of Mars, a rich history of observations and practical research has been accumulated on the surface of the red planet. It is worth dwelling on its stages. Polar glaciers. One of the similarities between the physical and climatic processes on Earth and Mars is the presence of icy continents in the polar regions. Mars ice cover varies depending on the season. If the north increases, the south decreases and vice versa. The diameter of the stable part of the main zones of the North Pole is 1,000 kilometers. The thickness of the ice shell is 3.7 kilometers. The maximum law field spread reaches 50 degrees south or north latitude of Mars. Interestingly, the Antarctic ice cap begins to smoke when it warms up. Due to the spring thaw, strange geysers are formed, which release streams of carbon dioxide into the planet's atmosphere along with sand, dust and mud. Seas and Manert. The red planet has a special feature, an important difference in the geologic structure of the regions south and north of the equator. The southern part is dominated by hills and has many craters. It is darker, marine. The northern part, on the contrary, smooth, light and low, continents. The reason for this striking difference is unknown. Experts believe that this could be due to the movement of lithospheric plates or due to a cosmic catastrophe. Dried rivers and deep wells. Examination of the Martian soil with special equipment gives the following evidence of its water resources functioning. Asterisk dry river streams. Asterisk river channels extending above ground. Asterisk the area of the river mouth near the Eberswald crater, an area of 115 square kilometers. Canals over 60 kilometers long. Asterisk minerals formed in water. Asterisk ice deposits. Asterisk fresh traces of salt water. Asterisk remains of dry water flow. Asterisk stones worked by the water. Asterisk a subglacial lake beneath the ice sheet, 1.5 kilometers deep. Interesting fact, wide and deep trenches have been found on Mars. Diameter and length over 100 meters. Soil. Without going into geological and chemical details, we can safely say that Martian soil is suitable for agricultural use. This is the opinion of the American expertess. Come out after several laboratory studies. The soil contains all the components necessary for cultivated plant life. Interesting fact, perhaps the most important and game-changing event in space exploration was the extraction of water from Martian soil by the Phoenix landing module in 2008. Why is Mars so named? Mars was named after the Roman god of war because of its red color. This tone really evokes associations with cruel and merciless battles. Later, both satellites of the planet received the names of the sons of Ares, Phobos Fear and Deimos Terror. Also, according to ancient Roman canons, the best time to start a war is March. It is clear where the name of the first spring month came from. Why is Mars red? The cause of the planet's reddish hue is iron oxide. Simply put, rust, which makes up most of the dust. It covers Mars in a layer from a few millimeters to 2 meters Tharsis Highlands. Iron oxide is lifted into the atmosphere by the wind, creating upward currents. It can be seen from space. In fact, the surface of Mars has a whole range of colors: yellow, brown, gold, brown, red, green. It all depends on the chemical composition of the soil. Spectral analysis of equipment on the Mars Express Interplanetary Space Station has provided a definitive answer to a riddle that has tormented the best minds of mankind for millennia. Storms on Mars. Mars' small size, thin atmosphere, and very low pressure combine to create constant winds. The planet is constantly blown by strong currents flying at a speed of 100 meters per second. They reach their maximum in early summer because of the huge temperature difference between the northern and southern hemispheres. The formation of Martian storms involves massive dust streams, which are weakly slowed down by gravity. The strength of the eddies swirling around the surface of our astronomical neighbor exceeds all known limits. From space, only the yellow clouds covering the entire planet are visible. The life expectancy of dust storms varies from 50 to 100 days. Sometimes, when passing perihelion, the closest orbital point to the Sun, the phenomenon becomes global. This happens much more frequently than expected, once every 188 Earth years. Dust devils. There is another interesting phenomenon that resembles an Earth tornado. Dust devils, also known as dust devils. They are dust towers that carry gases and water from the surface of Mars into the atmosphere with their vortices. There are millions of these vertical, violently rotating streams, A tornado occurs over an area of 1 square kilometer every few seconds. All that would be fine, but storms and tornadoes create static charges due to dust friction, which negatively affects technical equipment. During natural disasters, fine grains of sand can enter the device. They also cover the working surfaces of solar panels and optical instruments, thus preventing research equipment from working. Interesting fact, on February 13, 2019, the disintegration of the Opportunity rover, which finally ended the search, was a loss for all of humanity. Interest has been fueled by the latest dramatic report about the device on social media, which says the battery is low and a power outage is imminent. The rover operated on the surface of Mars for 15 years, but storms and cold weather robbed it of its ability to communicate. Mars attractions. Mars is full of unique objects. Some of them are unique in the entire solar system. Would-be travelers will find something on a neighboring planet. Even a simple list leaves a lasting impression. Olympus on Mars, of course. The most famous landmark is Olympus and its extinct volcano. It is 26 kilometers high and up to 85 kilometers wide. The crater has deepened to 3 kilometers. Mariner Valley Canyons. The canyons of the Mariner Valley are up to 3,000 kilometers long. Its pearl is the deepest gorge up to 8 kilometers high, called the Giba Canyon. The process of its formation is still a mystery. The Night Maze, named after its shape, is a system of canyons, a collection of long dormant Elysian volcanoes, strange morphologic structures, Medusa fossa, spider, lace, channel patterns. Frozen footprints of the fall are craters up to 16 kilometers in diameter. The sediments of the equatorial region are a particular mystery. They don't reflect radio waves. The infinite richness of shapes and landscapes of this unique planet can satisfy the taste of the most sophisticated futuristic artist. And the existing white spots of Mars are waiting for their discoverers. Is there life on Mars? A rhetorical question that has yet to be answered. There are several favorable conditions. Among them, the presence of water. The presence of methane and carbon dioxide in the atmosphere. Foil saturation with minerals and trace elements. Occasional positive temperatures. Electrical solutions. On the other hand, there are many unfavorable conditions. Due to solar wind and cosmic rays, the planet's surface has high radiation. Radiation levels on Mars are hundreds of times higher than on Earth. Constant water consumption. Low average temperature. Severe weather conditions. Storms, hurricanes, tornadoes. Chemicals that are incompatible with biological structures. There are no signs of microorganisms on Mars. There's no organic matter on the red planet. Interesting fact, a series of experiments were conducted to grow bacteria, algae and lichens in Martian conditions artificially in laboratories. The results are positive. One microorganism has been able to adapt to the new climate better than Earth's climate. Perhaps somewhere in the caves and crevices of Mars there were or are conditions for the origin of life. The question remains, the past and future of Mars satellites. The astronauts' opinions on the origin of the satellites are conflicting. It may have been asteroids attracted by the planet in the past. Their possibility during the collision cannot be ruled out. Scientists are unanimous about the future. Phobos is in danger of destruction, which could lead to the birth of a planetary ring around Mars. Its components are gradually reaching the planet. Deimos has a different point of view as it gradually moves away from Mars. Interesting fact, long before the American A. Hall discovered Phobos and Deimos in August 1877, their existence was predicted by D. Swift, F. Voltaire. The Anglo-Irish writer, creator of the famous Gulliver's Travels, reported the orbits and rotation times of the satellites in his book. Indeed, not entirely accurate. Grateful descendants wrote down the names of the visionaries and marked them into craters on the surface of Deimos. History of Mars exploration. The Egyptians began observing our nearest cosmic neighbor in ancient times. Later they were joined by the Babylonians, Greeks, Hindus, and Chinese. Arab astronomers also took part. Astronomical treatises and reports of the time focus on simple measurements and regular observations of the planet's movements. Medieval scientists brought harmony to the geometry of the solar system. Copernicus' heliocentric system created the sun and planets. Telescopes began a new phase in the study of Mars. Galileo Galilei was the first to master the technique of instrumental research. His work was continued by Giovanni Cassini, Tycho Brahe, and Johannes Kepler. Huygens and Schiaparelli's maps of the surface of Mars were published. The satellites of the red planet were found and accurate calculations were made. The work of astronomical observatories continues today. The launch of space rockets and equipment brought a new round of research. An era of competition between the Soviet Union and the United States had begun. Interplanetary space stations have been sent to Mars 39 times to explore the orbit, send probes, and Mars rovers. 8 delegations are currently active and 7 more are scheduled to arrive soon. Colonization of Mars between 2030 and 2033. The possibility of sending a spacecraft with a crew is being considered by the US, NASA, Russia's Roscosmos, and the European Space Agency, among others. The United Arab Emirates is developing the Mars 2117 project, a kind of future alien colony of Earth. Many private organizations are interested in the area. Elon Musk, founder of the SpaceX space company, is particularly active. He is actively promoting his business projects with financially promising aspects. The problems and difficulties are many, but the goals are incredibly attractive. Who wouldn't want to be the first human to set foot on Mars? Recruitment of space personnel is already underway. It is possible that some of the future astronauts will be able to repeat the famous small step of Neil Armstrong.
In the first fraction of a second after the Big Bang, the universe underwent a series of rapid and transformative events that set the stage for everything that followed. This period is known as the Planck epoch, during which the universe was extremely hot and dense, existing at temperatures above 10 to the 27 degree Kelvin. The fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were combined into one force in that brief moment. As the universe began to cool, it quickly moved beyond the Planck epoch into the grand unification epoch. At this time, the fundamental forces began to separate, and gravity became distinct from the other forces. The universe was rapidly expanding in a split-second process known as cosmic inflation, exponentially stretching space and smoothing out all the bumps. This phase of inflation allowed different regions of the universe to cross far apart, even though they had the same initial conditions. When inflation ended, the universe continued to cool and matter began to form. In the next step, known as reheating, the energy from inflation is converted into particle-antiparticle pairs, leading to the creation of many fundamental particles, including quarks, electrons, and neutrinos. Conditions remained so energetic that these particles could not yet form stable atoms, maintaining a soup-like state of free particles. About 1 second after the Big Bang, the universe expanded and cooled enough that quarks could combine in 2s and 3s to form protons and neutrons. This marked the beginning of the barrier genesis phase, where the matter that would eventually lead to stars and galaxies began its journey from this explosive origin. Understanding these early moments reveals the basis of our universe, explaining not only how it formed, but also why it took the form we see today. The formation of the first stars and galaxies in the early universe marks a pivotal moment in cosmic history, often referred to as the cosmic dawn. This process began after the universe underwent a period of cooling and expansion following the Big Bang, which occurred about 380,000 years after the original explosion. At this point, the universe has cooled enough for electrons to combine with protons to form neutral hydrogen atoms in a phase known as recombination. This led to the Dark Ages, when the universe became mostly transparent to radiation. As the universe continued to expand, small fluctuations in the density of matter left over from quantum fluctuations during inflation played a crucial role in starting the formation of stars and galaxies. Areas of slightly higher density began to gravitationally pull in the surrounding gas, which is mostly hydrogen and helium. Over millions of years, these dense regions collapsed under their own gravity, forming the first cosmic structures. Once the density reached a critical threshold, these clumps of gas formed protostars, leading to regions where matter collected and heated up. As the gravitational pressure increased, the temperature inside these protostars soared, eventually reaching the conditions necessary for nuclear fusion. This process ignited the first stars, often called the three-star population. These early stars were massive and short-lived, burning fuel quickly and producing vast amounts of energy that fueled the rionization of the universe. the intense radiation and stellar winds from these first stars had a huge impact on their surroundings, helping to clear large amounts of gas and dust, facilitating the formation of galaxies. These star clusters began to merge into larger structures, creating the basis for the galaxies we see today. Interactions between gravity, radiation, and cosmic evolution laid the foundation for the rich tapestry of galaxies that fill our universe. Through this intricate process, the primordial seeds of cosmic structure laid the foundation for everything from our own Milky Way to countless other galaxies scattered throughout space. Dark matter is a mysterious component of the universe, believed to make up about 25% of the total mass energy. Unlike normal matter that makes up stars, planets, and all life, dark matter does not emit, absorb, or reflect electromagnetic radiation such as light. This makes it invisible and only detectable through gravitational effects on visible matter and radiation. The existence of dark matter has been inferred from various astrophysical observations, such as how galaxies rotate and how clusters of galaxies behave under the influence of gravity. One of the key observations pointing to the presence of dark matter is the rotation rates of galaxies. According to Newtonian physics, the outer regions of galaxies should rotate more slowly than their inner regions due to the apparent mass distribution. However, astronomers have discovered that the outer parts of galaxies are spinning at unexpectedly high speeds, suggesting the presence of significant amounts of unseen mass, now identified as dark matter. Similarly, gravitational lensing, the bending of light from distant objects around massive galaxy clusters, provides another way to infer the presence of dark matter. The lensing effect is stronger than would be expected based solely on visible matter, indicating that there is much more mass than is visible. Dark matter interacts with ordinary matter mainly through gravity, but its exact nature remains elusive. Many theoretical candidates for dark matter include weakly interacting massive particles, or WIMPs, which would interact through the weak nuclear force in addition to gravity. Other candidates may include axions or sterile neutrinos, but neither has been definitively detected. Because dark matter does not interact electromagnetically, it does not form atoms or molecules, making it fundamentally different from the matter that makes up stars, planets, and living organisms. Research into the fundamental properties of dark matter and its possible interactions outside of gravity continues. Experiments designed to directly or indirectly detect dark matter particles are being conducted deep underground or in space, but so far none have produced conclusive results. Understanding the nature of dark matter is critical because it plays a vital role in the formation and evolution of structures in the universe, influencing the development of galaxies and galaxy clusters over time. The quest to find out what dark matter is one of the most significant problems of modern astrophysics and cosmology. The apparent predominance of matter over antimatter in the universe is one of the great mysteries of modern physics and cosmology. According to the fundamental laws of physics, for every particle of matter there must be an equivalent antiparticle. When matter and antimatter meet, they annihilate each other, producing energy in the form of photons. In the first moments after the Big Bang, both matter and antimatter should have appeared in roughly equal amounts. But our observable universe is mostly matter with very little detectable antimatter. This imbalance is explained by a phenomenon known as baryon asymmetry. Theories suggest that in the very hot and dense conditions of the early universe, processes may have favored the production of matter rather than antimatter. One leading explanation involves a term called CP violation, which refers to violations of the combined charge-pairing symmetry. In some particle decays, experiments have shown that the particles decay differently from their antiparticle counterparts, indicating an asymmetry in how matter and antimatter behave under certain conditions. Several models propose different mechanisms that could have led to this asymmetry. One of the most notable is electroweak baryogenesis, which suggests that at high energies interactions involving the electroweak force, one of the fundamental forces of nature, could have caused an imbalance between matter and antimatter. Another possibility involves certain theoretical particles, such as the Higgs boson, which may play a role in the predominant generation of matter. Ultimately, the exact process that led to the excess of matter over antimatter remains unclear. Researchers continue to investigate this question with experiments, looking for signs of baryonic asymmetry and particle collisions, the cosmic background radiation, and other cosmological phenomena. The study of this imbalance of matter and antimatter not only deepens our understanding of particle physics, but also addresses fundamental questions about the origin of the universe and the conditions that contributed to its evolution as we perceive it today. The answers may hold clues to understanding the fundamental structure of reality itself. Cosmic inflation refers to the rapid exponential expansion of the universe that occurred in the first moments after the Big Bang, from about 10 to the power of minus 36 to 10 to the power of minus 32 seconds. This remarkable phase of inflation helps explain some features of our universe, including its uniformity and the distribution of cosmic structures. While the exact cause of cosmic inflation remains an area of active research, there are several leading theories that provide potential mechanisms for this dramatic expansion. One popular hypothesis suggests that inflation was driven by a scalar field known as the inflaton field. This hypothetical field is thought to have occupied the early universe and created a negative pressure that in turn caused the rapid expansion of space itself. As the inflation in the field died down, it converted its energy into particles and radiation, which led to the subsequent cooling of the universe and the formation of the cosmic structures we see today. This process can be compared to the release of stored energy that propels the universe into a period of accelerated growth. Another aspect of cosmic inflation is how it solves certain puzzles in cosmology, such as the plane problem and the horizon problem. The problem of flatness concerns the exact balance of density in the universe. Inflation explains why our universe looks so flat today, stretching slight fluctuations from a highly curved state to a flat geometry. The horizon problem highlights the uniform temperature of the cosmic microwave background radiation over vast distances, even in regions that should not be in contact with each other. Inflation assumes that these regions were once close together before rapid expansion pushed them apart. In addition to these theoretical foundations, researchers are actively testing the predictions of inflationary models using observational data, such as measurements of the cosmic microwave background radiation and large-scale structural studies. While the exact mechanisms of cosmic inflation are still under investigation, this concept has fundamentally advanced our understanding of the early universe and the processes that led to the origin of the cosmos as we experience it today. This foundational phase of inflation not only changed the universe in its infancy, but also laid the foundation for the formation of galaxies, stars, and eventually life itself. The fate of the universe is the subject of considerable speculation and research within cosmology, and three main scenarios have emerged as to how it may ultimately end up: the Big Freeze, the Big Rift, and the Big Crunch. Each of these scenarios depends on the dynamics of cosmic expansion, the density of matter, and the properties of dark energy, which is believed to drive the accelerated expansion of the universe. According to our observations of the universe, the Big Freeze is currently the most widely accepted model. In this scenario, the universe continues to expand indefinitely further and further out into space. Over vast amounts of time, trillions of years, the galaxies will move away from each other, resulting in an increasingly cold and empty universe. Star formation will cease as the available gas and dust are exhausted, leaving only remnants such as white dwarfs, neutron stars, and black holes. Eventually, all the stars will burn out, and the universe will reach a state of thermodynamic equilibrium, filled mostly with low-energy radiation and dark matter, reminiscent of heat death. This long, slow decline is characterized by the universe becoming dark and cold. In contrast, Big Rip draws a more dramatic conclusion. If dark energy were to increase over time, it could exert a force that would eventually overcome the gravitational binding of galaxies, stars, and even planetary systems. In this scenario, the accelerated expansion accelerates to such an extent that it tears apart galaxies, stars, planets, and even atomic structures. The universe will end in a catastrophic collapse of everything into an infinitesimally small state, resulting in a chaotic and unrecognizable cosmos. Big Crunch presents another possibility. In this model, the expansion of the universe eventually slows down due to gravitational forces, leading to a reversal of the cosmic expansion. The universe then contracts, bringing the galaxies together until they collide and merge into an ever denser state. If this process continues, the temperature of the universe will increase dramatically, leading to an incredibly hot and dense singularity reminiscent of the conditions of the Big Bang. This cyclical view of the universe implies a potential rebirth, as the cosmos could theoretically re-enter an expansion phase after a collapse. Current observations, including measurements of cosmic acceleration and the effects of dark energy, lean toward a big freeze as the most likely outcome. However, as research continues and new cosmic phenomena are discovered, our understanding of the fate of the universe may evolve, providing a deeper understanding of the ultimate fate of all existence. Each scenario includes fascinating aspects of physics that not only explain the distant future of the universe, but also deepen our understanding of space, time, and the fundamental forces at work. The multiverse concept suggests that our universe may be just one of many different universes existing simultaneously, each with potentially different physical laws, constants, and properties. Although the concept of the multiverse has gained traction in some areas of theoretical physics and cosmology, it remains largely speculative and the subject of intense debate among scientists. There is no definitive experimental evidence to support the existence of multiple universes, making this a fascinating but unresolved question in modern science. Several theoretical frameworks propose different types of multiverses. One example is the inflationary multiverse, which arises from the theory of cosmic inflation. According to this idea, as the early universe expanded rapidly, different regions could have stopped inflating at different times, leading to bubble universes. Each bubble can have its own individual properties, and these bubbles can represent different universes within the larger multiverse. In this scenario, an infinite number of universes could exist, each with different physical laws and constants. Another concept is the many worlds interpretation of quantum mechanics, which states that every quantum event leads to branching universes. In this interpretation, all possible outcomes of quantum measurements actually occur, each in its own separate universe. This suggests a vast landscape of universes that includes all possible variations in the outcomes of quantum events. The total number of universes in a multiverse scenario is an open question, and can range from a calculated infinity to an unlimited number beyond comprehension. Some models even suggest that universes may be constantly forming and dissolving, further complicating the idea of counting them in any traditional sense. The implication is that if a multiverse exists, our understanding of reality as we know it may be fundamentally limited. While the idea of a multiverse offers intriguing possibilities and elegantly explains some phenomena in a theoretical framework, it also raises important philosophical and scientific questions. The multiverse hypothesis is difficult to test directly because other universes would likely be inaccessible to us based on our current understanding of physics. Thus, while the concept of life in the multiverse continues to inspire thought and debate, it remains an area rich in potential but lacking in definitive empirical evidence. Quantum entanglement is a remarkable phenomenon that arises from the principles of quantum mechanics, where two or more particles are entangled in such a way that the state of one particle instantly affects the state of the other, regardless of the distance between them. This phenomenon challenges our classical intuition about how particles interact and has led to profound questions about the nature of reality, space, and time. When particles are entangled, measuring the state of one particle directly affects the state of the other, even if they are light years apart. Albert Einstein described this phenomenon as eerie action at a distance. Einstein, along with his colleagues, initially saw this entanglement as problematic for local understanding of physics. However, numerous experiments, beginning with those of Alan Aspect in the early 1800s, have confirmed that entangled particles do indeed exhibit this instantaneous correlation, regardless of spatial separation. The exact mechanism behind this instantaneous coupling remains one of the greatest mysteries in quantum mechanics. The implications of quantum entanglement for our understanding of spacetime are profound. Entanglement implies non-locality, which contradicts the classical notion that information cannot travel faster than the speed of light. This has led to a rethinking of how scientists understand the structure of space and time. Some interpretations suggest that entangled particles may point to a deeper interconnectedness of the universe, challenging the idea that space-time is fundamentally separate and distinct for each individual particle. In addition, quantum entanglement plays a significant role in new theories of quantum gravity, where physicists seek to unify general relativity with quantum mechanics. Some researchers suggest that space-time may arise from the entanglement of fundamental quantum particles. From this perspective, the fabric of the universe could be woven from entangled connections between particles, suggesting that what we perceive as space-time may be an emergent property of these underlying quantum states. Researchers continue to explore the implications and mysteries of quantum entanglement through various experiments and theoretical advances. Its connection to fundamental concepts in physics not only redefines our understanding of the quantum realm, but also challenges existing paradigms of how we conceptualize reality itself. As scientists probe deeper into the intricacies of entanglement, they may uncover insights that could change our understanding of the universe at its most fundamental level. Primordial black holes are a fascinating class of black holes thought to have formed in the very early universe, shortly after the Big Bang. Unlike stellar black holes, which form from the gravitational collapse of massive stars at the end of their life cycles, primordial black holes may have formed from density fluctuations in the hot, dense environment of the early universe. As the universe expanded and cooled, regions of space with higher density than average could collapse under their own gravity, leading to the formation of these black holes. Conditions prevailing in the early universe were extreme, with high energy density and rapid expansion during the inflationary era. During this time, quantum fluctuations could be amplified to macroscopic scales, leading to significant variations in density throughout the primordial cosmic soup. If some of these fluctuations reached a sufficient critical density, they could undergo gravitational collapse to form black holes before stars, galaxies, or other large structures had a chance to develop. This mechanism allows for the existence of primordial black holes with a wide range of masses, from very small ones, perhaps only a few times the mass of a small asteroid, to much larger black holes. Primordial black holes may play a unique role in the evolution of the universe. On the one hand, they can act as seeds for the formation of galaxies and large-scale structures. Their gravitational influence could pull in the surrounding matter, contributing to the processes of galaxy formation. This aspect raises intriguing questions about how these black holes can interact with their surrounding matter and influence cosmic evolution. In addition, there have been speculations about the connection between primordial black holes and dark matter. Some theories suggest that these black holes may make up some or even all of the dark matter that permeates the universe. This hypothesis is intriguing because it could shed light on the elusive nature of dark matter, which is currently understood largely through its gravitational influence on visible matter. The quest to understand primordial black holes encompasses ongoing observational efforts, including studies of gravitational waves and the search for potential signatures of these black holes in cosmic structures. These studies could lead to breakthroughs in our understanding of the early universe, the processes by which black holes form, and the role they play in shaping the cosmos we see today. As researchers continue to investigate these enigmatic objects, primordial black holes open up a rich field of research at the intersection of cosmology, astrophysics, and fundamental physics. The cold spot in the cosmic microwave background, a remnant of the Big Bang, is a fascinating puzzle for scientists. This particular region is much cooler than the surrounding areas, with slightly below average temperatures. One of the leading theories to explain this phenomenon is the possibility of a large supervoid, a vast expanse of space with far fewer galaxies than the average. If such a supervoid exists, it would be millions of light-years across, and would have less matter to contribute to the gravitational effects that regulate temperature. Another intriguing hypothesis considers the possibility of primordial fluctuations in the density of matter in the early universe. These fluctuations would affect the formation of cosmic structures and could lead to changes in the temperature of the cosmic microwave background. Some researchers believe that the cold spot may be the result of an unusual cosmic event or the remnants of the gravitational influence of an ancient supercluster that left its mark on the fabric of space-time. Additionally, there is a theory that explores the implications of other universes. Speculations surrounding the multiverse suggest that our universe may be just one of many. If another universe collides with ours, it could cause disturbances in the cosmic microwave background, potentially showing up as cold or hot spots. This concept pushes the boundaries of our understanding and calls for further research and exploration. As scientists continue to study the cold spot, it reminds us of the complexity of the universe and the challenges we face in piecing together its history. Each discovery not only helps shed light on the origins of our cosmos, but also raises deeper questions about the nature of reality itself. The WOW signal, detected on August 15, 1977, is one of the most intriguing developments in the search for extraterrestrial intelligence. This strong radio signal came from the direction of the Sagittarius constellation and lasted for 72 seconds. It was recorded by a radio telescope at Ohio State University, and the intensity of the signal was so amazing that one of the astronomers, Jerry R. Amon, wrote the word WOW in red ink on the printout, giving the signal its catchy name. What makes WOW? The signal is particularly exciting in that it matches an expected signal that may be made by an alien civilization. It had the correct frequency, which was in the range of hydrogen, a key element in the universe, and a frequency commonly monitored in search of extraterrestrial messages. Despite subsequent investigations, the signal was never definitively replicated or traced to a specific source, leaving a cloud of mystery surrounding its origin. Several theories have been proposed to explain the signal. Some believe it may have been a natural phenomenon, perhaps related to a comet or other astronomical event. However, these theories struggle to explain the narrow bandwidth and unique properties of the signal that closely match those of an artificial origin. Others suggest that it may have been a transmission from an extraterrestrial source representing an advanced civilization attempting to communicate across the vast distances of space. The lack of a clear explanation for the WOW signal has fired the imagination and fueled ongoing debate in the scientific community. As technology advances and our understanding of the universe expands, the mystery of the WOW signal continues to challenge researchers to explore the vast possibilities of life beyond our planet. It's a reminder of how much we still have to discover about our universe and the potential neighbors waiting to be discovered. The formation of organic molecules on Mars is an area of great interest to scientists, especially in the search for past life on the planet. Organic molecules are the building blocks of life as we know it, which consists mainly of carbon and can include many other elements such as hydrogen, oxygen, and nitrogen. Evidence suggests that these molecules may have formed through a combination of processes, both biological and abiotic, during the ancient history of Mars. One of the important sources of organic molecules is the geology of the planet. Mars is known to have once had a wetter and warmer climate with conditions that could have favored chemical reactions that may have led to the creation of simple organic compounds. Laboratory experiments have shown that under the right conditions, for example, in hydrothermal systems or in the presence of certain minerals, organic molecules can form. These reactions could have occurred in Martian soil or subterranean habitats. In addition to geological processes, the detection of organic molecules by missions such as the Curiosity rover opens up intriguing possibilities. Curiosity discovered complex organic compounds in sedimentary rocks, suggesting that if life once existed on Mars, these molecules may contain its remnants. However, these organic compounds can also result from non-biological processes, such as the interaction of carbon-rich materials with UV radiation or cosmic rays and thermal events. Although the presence of organic molecules indicates the planet's potential for life in the past, they do not provide conclusive evidence. An exciting idea is to understand whether these molecules could be remnants of ancient biological activity or simply the result of natural chemistry. Future missions, such as the Mars Sample Return mission, aim to collect samples and return them to Earth for further analysis. This would provide important insight into the question of whether life ever flourished on Mars, enriching our understanding of the planet's history and the broader search for life elsewhere in the universe. Astronauts report that they experienced mysterious flashes of light during space flights. This phenomenon has baffled scientists and captivated the public. These flashes often occur in the dark, such as during spaceflight or when passing through the Earth's shadow. As strange as they may be, they are believed to be the result of cosmic rays interacting with the human eye. Cosmic rays are high-energy particles, mostly protons, that travel through space and are a natural part of the space environment. These particles come from a variety of sources, including supernovae and the Sun itself. When cosmic rays enter the protective environment of a spacecraft or spacesuit, they can collide with atoms in an astronaut's eyes, creating a cascade of secondary particles. This interaction can cause a reaction in the retina, creating the sensation of a flash or streak of light. This phenomenon is similar to the visual sensations experienced by people undergoing a medical procedure called a retinal scan, in which direct exposure to the retina can cause similar flashes, even without actual light. Also, the lack of an atmosphere in space means there are no particles or air to scatter the light in the same way as on Earth, making these flares particularly noticeable to astronauts. Research into this phenomenon has improved our understanding of the dangers associated with spaceflight. Frequent exposure to cosmic rays may contribute to long-term health risks, including increased rates of cancer and potential damage to the nervous system. As space exploration continues, astronauts will need to remain alert to these flares and understand their health and performance implications during missions, especially long-duration journeys to places like Mars. This ongoing investigation not only unravels the mysteries of the human experience in space, but also highlights the challenges facing